Good day, everyone. My name is Rubanga Kene Emmanuel Brady, and today I'll be presenting our project titled Incentivizing Clean via a Low-Cost Sensor Network with Spatial Temporal Air Quality Monitoring in Uganda's Informal Food Spaces. This work focuses on the health risks of air pollution in small restaurants and food stalls, and proposes a system that combines low-cost sensors, data analytics, and incentive mechanisms to encourage cleaner practices. I'll walk you through the background related works, the problem statements, and the technical approach behind the whole project. So without wasting time, let's get into it. Before we go any further, I'd like to talk about the background and the introduction, and a bit about the introduction of the project at hand. Air, air pollution in restaurants and chapati stores across Uganda is a crucial but often ignored health issue. Customers usually spend 10 to 30 hours during peak restaurant hours in such environments, and these spaces normally lead to such customers getting exposed to smoke, carbon dioxide, nitrogen dioxide, and fine particles. These pollutants mainly come from the common sources for such pollutants include charcoal stoves, open frying, and poor ventilation. I beg your pardon, such exposures raise respiratory health risks in general. This project proposes a low-cost sensor network to monitor air quality in real time and provide incentives to maintain a cleaner air. Yeah. The related works, the recent trends, and literature review. Recent studies show that low-cost air quality sensors are increasingly used in resource-constrained regions, though calibration and reliability remain major challenges. Spatial temporal modeling approaches have been applied in urban areas to capture exposure trends, but informal food spaces are rarely studied. Incentive-based interventions have been proven effective in driving behavior change in public health, yet very few projects combine air quality monitoring with real-time feedback and economic rewards. This project will address the gap. This project will address the gap merging sensing, modeling, and incentives into integrated systems tailored for Uganda's informal food economy. As you can read through it on the screen behind me, if you could just pause the video and look at it as well. Obviously, as we talk about this, there are problems that can arise from air quality, poor air quality, and some of the problems there are domain application problems and computational problems. For the domain application problems, some of the problem statements that may arise are air pollution in informal spaces lead to respiratory health issues. Obviously, like in the beginning sense, there is cough, there is flu that can arise due to such, and in extreme cases, it can even lead to suffocation. Um, you might develop sinuses due to such situations. Anyway, I'm getting driven away from the topic. Another problem is lack of cheap and reliable monitoring tools in Uganda. Yes, Uganda is first of all a third world country, so having access to such tools for monitoring and censoring air quality is kind of hard to reach. And then there's the absence of structured incentive mechanisms to promote clean practices. And there's also that. Then some of the computational problems that arise are obviously there's also noisy data and noisy and irregular data that's difficult to handle. Then there's performing spatial temporal modeling for short-term exposures. Another problem that can arise is designing an explainable composite score. Also, in layman terms, I can say an itself score. So to actually calculate the score of an environment, you might need the how congested it is, how much ventilation it has, and how busy it is. Obviously, that's a part of congestion. All of those factors affect the computational problem of designing an explainable composite score.
So, anyways, in this mark, I want to take you through a dataset description and exploratory data analysis. So now, we're dealing with the database of hourly PM 2.5 and PM 10 air quality observation from 68 monitoring stations in Uganda between 2019 and 2020 using both low-cost and reference-grade devices. So, the main reason why we chose this database is because since we're doing air quality, we needed data that was highly detailed and more specific. We needed data that was air quality data that was recorded over short time intervals, and unlike other data that were giving us time intervals of a year, but spanning over multiple years, we couldn't choose those ones because we needed very short time intervals. And another reason why we chose this one is because it was giving us specific geographical locations in the country that we can use to predict other locations of or other air quality values in other locations. So yeah, the structure of the dataset consists of 6 columns, one being the site ID, site longitude, site latitude, and timestamps PM 2.5 and PM 10. So we carried out data cleaning, but luckily for us, our data did not have any missing values. As you can see, it didn't have any missing values. So we continued to carry out a statistical summary of the dataset to see the kind of data we're dealing with. And as you can see, it showed that we have around 500,000 rows of data. And like in the row of PM 2.5, you can see it starts all the way from the minimum of 2.7 all the way to a maximum of 214 with a mean of 37. And the same for PM10 that shows us where it starts from 1 all the way to around 500 with a mean of 50. Now to see a visualization of this data, one could start with the histogram that shows us the distribution of the PM 2.5 over all the 500,000 rows of data. As you can see, the graph is tending towards the left. That shows us that majority of the year we're having moderate and good air quality of the entire year, except for the extreme conditions where we're reaching around 200 micrograms of air. Except for those extreme cases, the year was generally having good air quality. The same can be said for PM10 because we expect them to be similar since they are correlated. So when the distribution should be similar to each other. So since they are correlated, like I said, so we'd expect that since PM 2.5 particles increase, then we'd expect the PM10 particles to also increase. And as you can see, since we're starting from the low values, you can see that it's following that trend. You can see that as it's increasing, so the PM10 is increasing, except for now the higher values of PM2.5, where now we start to see the PM10 stray away from the trend. This could be due to some environmental factors or other factors that can affect the PM2.5 particles, but they can't affect the PM10 factors, such as like environmental factors, let's say like introduction of a dust storm that introduces a large amount of PM10 particles. Since dust is slightly larger particles, so we expect an increase of PM10 particles, or increase of let's say traffic due to the increase of population. Then also when the traffic increases, we'd expect the PM10 also to increase. So now these factors, they stray away from the trend, since PM 2.5 is just a subset of PM10, so that's why we'd expect it to increase as it increases, so the PM10 increases. But if those factors are coming into play, then we'd expect the PM10 particles to increase more than expected. So now, as you can see, another graph is this box plot graph that shows us the distribution, as the concentration of the PM2.5 and the PM10. As you can see already, just on near view, you can see that the PM10 particles already, it is a higher graph. So that means there are more PM10 particles in the environment than the PM2.5. And like I said, since it's the PM2.5 is a subset of 10, of course we'd expect them to be higher. There's no way to expect the PM2.5 to be more because they are a subset, or that the PM2.5 are also part of the PM10 particles. But on seeing here, we're seeing extremely a lot of outliers. These outliers could be so many, like I said earlier, how we can have some environmental factors that introduce particles that we did not account for. So all these are the multiple outliers. That also proves what we had talked about in the other scatter plot graph. It shows that if those increase of PM2.5 particles are, they can, if the artificial machine learning models to consider all of them, then we wouldn't get accurate data. So that's why, since the data that we're dealing with is multi-correlated, we need to concentrate on only one variable, and of course we shall, since the PM2.5 particles are smaller and more dangerous to a human health, we would of course consider those ones to train a robot and predict the outcome of the air quality scores.
Hello, today I'm going to explain how I trained and evaluated my AI model. And our goal was to predict PM 2.5 levels so that our AI project called Incentivizing Clean Rating can rate restaurants based on their local air quality. The dataset is tabular and includes numeric features like hours, months, set latitudes and longitudes, and even PM10 concentration. So the model I chose, the random forest regressor, because it handles nonlinear relationships well. It needs very little processing and can naturally rank which features are most important for the prediction. That makes it a very strong and interpretable choice for the AI project. The model is a random forest made up of many decision trees, and for this particular one I used 100 trees, which is common for the starting point, and set the random seed to 42 to make it reproducible. And then the n job parameters was set to -1, and this was so to enable the model to use all CPU cores and train quickly. And then I split the data into 80% for the training data and 20% for testing, so that we can fairly evaluate performance of the unseen data. To measure accuracy, I used 3 standard regression metrics, and one was the mean absolute error, OMAE, which shows the average size of our prediction errors in micrograms per cubic meter, which is very easy to interpret. Then the second one was the mean square error, MSE, which penalizes large mistakes more heavily. This helps us to catch big misses easily. And then there is the R squared score, that's the R2 score, but it's actually R squared score, tells us how much of the valuation in PM 2.5 our model explains, basically the overall goodness of it. And then on the test data, the model achieved an MAE of around 3.15, and then an MSE of 51.054 approximately, and an R2 score of 0.959350. So this means that the model explains roughly around 94% of the variance PM 2.5 levels, which is a very strong performance. So when I looked at When I looked at feature performance, the M10 concentration stood out as the top predictor, and then followed by the time features and the location. And then the limitations can be, for example, extreme pollution spikes that are not present in the training data, which may be harder to predict. But overall, the model is accurate enough for our AI project and based on air qualities to rate the local restaurants.
Well, on to the conclusion. The project combines a supervised and unsupervised learning, where supervised modules predict the itself score from sensor data and unsupervised methods detect anomalies in pollution patterns. If realistic naturalistic intelligence because it reflects realistic naturalistic intelligence because it focuses on environmental and health related insights. The system applies clarification, clustering, and anomaly detection while representing knowledge through embedding rule-based thresholds and probabilistic reasoning. Philosophically, it aligns with weak AI since its task force and context limited, relating more to a practical decision support than a strong general intelligence. Some of the limitations that arise are sensor reliability. Low-cost sensors may drift over time. Connectivity issues. Now, this is in areas areas that are kind of remote. There will be an for there will be obviously unstable internet, and those unstable internet can lead to poor data being can lead to bad data mining. There are also calibration needs, frequent validation against reference grade devices. Also, also these are one of the limitations. And then there's context scope, only measures air quality and crowding, not other health risks. Then adaptation barriers. Restaurants may resist due to high costs, ignorance, and trust. Yeah.